All right, so last week we were talking about centripetal force. We looked at bank curves and unbanked curves as examples of those. These are much simpler than those. Okay, we have an intake fan blade on a jet engine that has a mass of 7.5 kilograms. So they gave us M, being 7.5 kilograms. Okay, as it spins, the middle of the blade has a speed of 365.9 meters per second. Okay, and it is 73.7 centimeters from the axis of rotation. I need that to be in meters. All right, we're looking for the centripetal force acting on the blade. So Fc equals mv squared over r. Okay, so that'll be 7.5 times 365.9 squared divided by 0.737, and we should get 1.36 times 10 to the 6, okay, newtons, right? Is that a lot? It's a lot, yeah. Okay, you got to build those things pretty strong, okay, in order for them to take that. All right, and then for number 2, okay, it's looking for the speed of the pebble that's stuck in the treads of a dirt bike's wheel, okay, and they give us the radius. Again, they give it to us in centimeters, so we need that to be in meters, 0.23 meters. So Fc equals mv squared over r. We're solving for v, so we multiply both sides by r, divide both sides by m, and then square root to get v. Okay, we plug in our numbers, we're going to get 8.5 meters per second. Everybody right with that one? Okay, I think we did that one on Tuesday, right? Pretty sure. And we did number 2. So I want you guys to try number 3, because I know we did number 2 on Tuesday. So okay, number 3 is just asking you to find radius. Okay, number 2 is asking what the coefficient of friction was. So you still have an unbanked corner here for this radio control car, right? Keep in mind that what units they give you the mass in, okay? And I'll give you a couple minutes on that one and we'll go through it. Okay, so to do a unbanked curve question, what do I have to remember about an unbanked curve? Right. The only thing keeping me from sliding off into the ditch is the force of friction. In other words, friction is acting as my centripetal force. Okay, so that means that mv squared over r equals mu times the normal force, which, because it's an unbanked curve, is equal to force of gravity, right? M times g. Okay? All right. So for this one here, we are looking for the radius of the turn. Now the problem is that radius is on the bottom here, and I can't solve for something when it's on the bottom. I need it to be on the top. So I'm actually going to multiply r over to this side, and then I'm going to divide everything by mu mg. M is going to cancel, and I'm just going to have mu g on the bottom here. So I'll have v squared over mu times g equals r, which will equal 3 meters per second. So 3 squared, okay, and then divided by the coefficient of friction, so 0.9 times gravity, 9.81. So the fact that they gave me the mass in grams actually doesn't matter at all because I don't need it, okay. That means that R will come out to 1.0 meters. Okay. Everybody all right with that? Now, let's just do a quick bank curve review here because we haven't talked about that yet. Okay, so write this one down as just a quick bank curve review. Okay, so we have an exit ramp banked at 6.5 degree angle, radius of 85 meters. At what speed can it be negotiated if it is frictionless? And all the bank curves we do are going to be frictionless because bringing friction in makes them a lot more complex. Okay, what things affect a banked curve? Speed, radius, and angle of bank. Those are the three things. Okay, remember our banked curve formula looks like this. Tan of theta equals v squared over r times g. Okay, all curves, banked or unbanked, are dependent on speed. Okay, for the angle of bank anyway. The angle of bank is dependent on speed, radius, and gravity. Okay, in the same way that when we look at an unbanked curve, the thing that keeps us in the curve is solved for in exactly the same way. Okay, so if we have this, sorry, I should show you how I arrived at that. Okay, mv squared over r equals mu, okay, times the normal force, mu mg. Okay, so if I'm looking for mu, I divide both sides by mg. Okay, the m's cancel. It's the same formula, right? Okay, so it doesn't matter what kind of a curve I'm taking. Either the coefficient of friction is dependent on speed, radius, and gravity, or the angle of bank is dependent on speed, radius, and gravity. Okay, that's kind of how all of those work. For a banked curve, though, that's the kind we're dealing with right now. This is the formula we have. Okay, v squared over r times g, and we're looking for v. Right, so in this question, they gave me the angle of bank, 6.5 degrees. Okay, they gave me r, 85 meters, and I always know g, so can I solve for v? Okay, so I need to get v by itself. What do I do with r and g? Multiply them both over. Okay, so I'm going to have the tan of theta times r times g equals v squared. I only want v, so I'm going to square root that. So that'll give us then the square root of the tan of 6.5 times 85 times 9.81. That will give us our speed. All right, well, we're not going very fast around that corner. Okay, 9.75 meters per second. That's a pretty typical bank curve. Okay, most exit ramps, okay, at least in the city, are pretty low speed, around 40 usually. Okay, and they're about that size. Okay, so that's a pretty realistic banked curve. Especially if they're frictionless. I mean, most of them have a speed of 40 because there's always some friction, of 50 because there's always some friction to depend on. All right, is that ringing the bell for everybody? How those work? Okay, so what I want to do today, for most of the period anyway, is just do some practice on centripetal force problems. Okay, so that'll be stuff out of the workbook. I'll put it up here in just a minute. Okay, but near the end, I'm going to start the lesson we're going to go through tomorrow, but obviously tomorrow's Friday, it's a shorter period. Okay, so I'm going to start it at the end of, near the end of class today so we get into it and then finish it tomorrow. Okay. No, sorry, tomorrow we're doing a lab. I guess I said that. We're doing our lab on speed and radius tomorrow. Okay. On Monday, we'll be doing a different lesson, but okay, we'll start a bit of it today. All right, so out of your workbook, okay, so you're working on just page number 2 here, guys, centripetal force problems. Okay, the answers are in brackets in bold after each question, so you can check as you go, right? So there's, some that are bank curves, some that are unbanked curves. Okay? And then it gets a little bit more into thinking them through a bit by the time you get to like question 9. Okay? But they're all basically curves and unbanked curves, okay, until we get to vertical circular motion. Right? So if you can be working on those, I'll make those a little bit bigger in case you're actually using them off the board here. Okay, there you go. If you're having trouble, just let me know and I'll come and help you. Okay, so for question number 2 here, it's actually asking about centripetal acceleration, which is solved for using this formula here, v squared over r. Okay, but what I want to show you is something you're going to have to do in this unit later on, and that's substitution. Okay, you're going to have to be able to substitute a formula in for a variable, okay, in another formula before the end of the unit. So we're going to use this question to kind of look at how we might do that. The reason we have to do that in this question is we're not given v, and it's the only way we can get a. All right, so the stuff we are given is we're given radius, 3,282 meters, and we're told the period is 2 minutes. Do we want that in minutes? No, we definitely want that in seconds, so 120 seconds. All right. Now, as I said, they don't give me v, but I do have a formula that solves for v, okay? And that's 2 pi r over t. Now, what I assume most people do on this question is they just plug these numbers into that formula, get v, and then square that number and stick it in this formula. And there's nothing wrong with that. But later on in this unit, there's going to come a point where with certain types of satellite motion questions, you won't be able to use formula A to get something you need in formula B. You'll actually have to substitute formula A into formula B because it's the only way you can make it work, and one of the things will cancel off. Okay? So if I want to substitute this formula for V into this formula for V, okay, what do I first need to do to it? In this formula, V is squared. So what do I need to do to that formula? Square it. Square everything in it. So what's 2 squared? 4. What's pi squared? Pi squared. It's a trick. Okay? What's r squared? Also a trick. R squared. And so forth. Okay? That's that formula squared, okay? Now, if I take that, I can just substitute it in to this formula, okay? I just plug it in place of v, so it'll look like this, okay? 4 pi squared r squared over t squared times r. Okay? I've just plugged it right in to that formula in place of v. Now, what one thing do I need to do before I start the next step? I've got r squared on the top and r on the bottom. What will happen? Okay. R squared divided by r is r. Okay. So now I can just plug my numbers in directly. Okay. I can go 4 times pi squared times 3,282, okay, divided by 120 squared. Okay, and when I do that, I should get my 9.0 meters per second. So 4 pi squared times 3,282, okay, divided by 120 squared. Okay, 9 meters per second squared for our centripetal acceleration. Right? Now, like I said, you didn't have to substitute to solve that one. You could have done it in 2 steps. But like I say, it's not a bad skill to start working on because it will be necessary later on in the unit when we do satellite motion questions. You will have to substitute that. Okay. Any other ones giving us trouble so far? Okay. Keep going then. All right, so now we're going to look at applications other than curves, like banked curves and unbanked curves, of uniform or horizontal, okay, circular motion. Now, we talked, when we first started talking about this, we talked about that ride at like Callaway Park or the Stampede, the Gravitron, and one that spins and pins into the wall, okay? Well, there's another application of that, and if you've seen any like kind of more modern science fiction movies, you've seen it used. How artificial gravity is generated. Okay? Now, it's not just science fiction. We could totally generate artificial gravity, in this way. Have any part of the station or ship be a spinning drum. Okay? As long as that drum is spinning, it will generate artificial gravity. Not real gravity, okay? But artificial gravity. That means if you stand on the inside of the drum, your inertia wants you to leave the drum in a straight line. But the drum stops you, which means it pushes on your feet towards the center. And it feels just like real gravity. Right now, I can feel the floor pushing on my feet. And I would feel the floor of the spinning drum push on my feet as well. Okay? It would make it feel like there's actually gravity. And as a result, I wouldn't have any of the health problems associated with being in zero gravity. Being in zero gravity is really bad for you. Okay? It's really, really bad for you. Okay? The human body was not designed to be without gravity for extended periods of time. Okay? All kinds of rotten things can happen. In fact, the first few days for an astronaut on the International Space Station are awful. They spend a lot of the time being green. Okay? Just feeling horribly nauseous, dizzy, arthritic, okay? All of these things while their body slowly adjusts. Okay? Because normally on Earth, okay, all of the fluids that are normally in our body kind of get pulled by gravity downwards. All right? And so they're more in our feet and our legs. But when that fluid isn't being pulled by gravity, okay, it redistributes itself everywhere. And you feel congested, okay, like a stuffy nose and head, except when it doesn't really run, it just feels, you feel pressure, you have a bad headache, okay? Your joints will feel sore, okay, arthritic, because more fluid is in your other joints, okay, and it kind of collects there. And for the first few days in zero gravity, you look swollen, okay? It looks like you went a few rounds, okay, with somebody who knew how to hit you, okay? Your face is actually puffy because that fluid is being redistributed. It takes a few days for your body to reabsorb it all and for you to kind of look a little bit more normal. After a while, you actually start to look a little bit skeletal, okay, like almost emaciated even. I'll show you some videos of Chris Hadfield. Like, he looks quite thin, okay, in a lot of those videos, and that's because he was on the International Space Station for a long time, and they do suffer, even with all the stuff they do, a lot of muscle loss and bone loss, okay? Because your bones need to be beat up on a regular basis in order to stay strong, okay? The first thing they tell an elderly person with osteoporosis is they tell them they need to do more weight-bearing exercise, and that can be as simple as going for a walk. Okay? As you go for a walk, okay, or you lift things or stuff like that, you cause microfractures in your bones. Okay? Those microfractures heal, and when they heal stronger. Okay? It makes your bones stronger to actually put them under stress. Okay? If, for example, if you've ever seen like a martial artist who breaks boards and bricks and stuff like that with their hands or feet, okay, that's not something you or I could just up and walk up and do. Okay? Even if we had the technique perfect, not doing it on a regular basis is going to mean that our bones are not sufficiently strong enough to pull that off. Okay? Someone who regularly breaks wood or breaks bones with their hands causes a lot of microfractures in the bones, and the bones become more and more dense, and it actually makes them harder and tougher, okay? And they're more likely to be able to do stuff like that without hurting themselves. Okay? Well, in zero gravity, you don't have gravity constantly causing all these little microfractures and stress on your bones. So your body starts to pull the calcium, okay? And your bones become lighter, less dense, okay? When Chris Hadfield came back from being in space for, 6 or 8 months he was up there, okay? His bone density was way down. He was like a frail old man in terms of his bone density, just because he had been in zero gravity for so long. Okay? It takes them a while to get that back. Similarly with your muscle. Okay? If you're in zero gravity, how hard do your muscles have to work to do stuff? Not hard at all, right? When you're in zero gravity, everything's weightless. Okay? So you don't have to work very hard, and your muscles start to deteriorate. Okay? Just like anything else. I mean, if you've been working out madly twice a day for 5 years and you get pretty jacked, okay, and then you just quit, what happens to your muscle mass? It just goes away, okay, because you're not using it anymore, right? And that same thing happens to astronauts if they're in zero gravity for too long. And the really worrisome part is, it's not just their like skeletal muscles, it's their heart and their lungs. Okay, the muscles that help them to ventilate their lungs get really weak, because normally on Earth, you're pulling your whole rib cage, collarbone, and everything up against the force of gravity in order to inflate your lungs, and then you just relax your lung muscles and everything kind of squeezes your lungs and you exhale. In zero gravity, that's not the case. Okay? You're not constantly working against that force of gravity, and as a result, even your breathing muscles can weaken. Right? Back when the Soviet Union crumbled, they had some of their astronauts stuck on Mir, the Russian space station, and they were stuck there for over a year. When they came back, they could barely breathe. They almost died. Okay? Like they had to be put on respirators when they came back, because they had been in zero gravity for so long that their muscles had totally atrophied, and they could no longer breathe. Okay? So it's a big deal. If you're going to be on a space voyage for a long time, like let's say you're going even to Mars, you don't want to be getting to Mars, and when you get there, you're so weak and frail that you fall down the ladder, okay? And instead of having some nice Neil Armstrong one small step moment, you get a face plant. Okay? That would be bad. Right? There's also all the sensory issues that go along with being in zero gravity. A lot of our senses, especially balance, are dependent on gravity. Okay? Our body knows which way is up and down even when we tilt ourselves, okay? Because of the pull of gravity. Okay? You've got all that stuff in your middle ear. Okay? That's why if you get an inner ear infection, you kind of get dizzy and kind of have poor balance. Okay? So in zero gravity, that just doesn't work. And that's why astronauts feel nauseous for days after they get there. Okay? It's because once they're in zero gravity, their middle ear is like that car alarm that won't shut off. It's screaming at their brain constantly. Oh, we're falling, we're tipping, we're upside down, we're right side up, you're leaning, and it's constantly telling the brain things that are wrong, because the middle ear is just freaking out. Okay? It doesn't know what's going on, because all the stuff that it normally relies on to tell you your orientation is just haywire. Okay? And so eventually, what happens is astronauts, their brains just shut it off. Okay? They stop listening to the balance center that's in the middle ear, and they start listening to, oddly, the eyes. The eyes become the organ for balance, which is fine in zero gravity, but really bad when you return to gravity, because it takes a while for the brain to start listening to the ears again after that. Okay? And so what happens to astronauts is when they've been in zero gravity, they depend on their eyes for balance, and they have really bad habits as a result. When they look one way, they lean that way. Okay? And they fall over really easily. Okay? That's why you never see an astronaut unaided when they first land. Like when the space shuttle used to land, okay, they would come down the step ladder and they'd have like a white knuckle grip on the railing. Okay? And when they walk down the hallway, they have somebody on either arm, okay, walking them down the hallway. Because if they didn't, they'd look drunk. Right? And the worst thing it could be doing is they're walking down the hallway and somebody from behind them calls their name. Okay? They'll go like this and they'll fall right over. Okay? Because as soon as they turn their head, their brain is going eyes for balance, and you turn like this and the body's like, you're falling! Boom! Yeah, you're falling. Yeah, because you weren't falling, but the brain thinks you are, because suddenly your eyes went this way and it went, body going that way. And down you go. Okay? It relies on something that's not supposed to be used for balance. In zero gravity, it's great because your references are all over the place. There is no up and down, not a problem. You can't fall. Okay? You return to gravity, you fall easily. Okay? And they did actually some tests with Chris Hadfield when he returned. Okay? He had to do a driving simulator, not a real car, for obvious reasons. Okay? So he's driving in the simulator, and every time he would look to the simulated mirror, he'd crash. Okay? Because he would steer right over there. Okay? He'd look, or he'd look at something on one of the side screens, and he'd just go that way. Okay? It takes them a while to get used to that. Okay? The other thing they get used to is just how objects behave in zero gravity. Okay? I was watching an interview. He was doing an interview on like a talk show or something, and the guy wanted his autograph. So he gives him the pen. Chris writes his autograph, and then he goes like this. Because for 6 months, if he went like that, pen would stay there. He's like, just goes like this and the pen falls. It's like, yeah, stupid gravity. Okay, like you just get used to certain things working a certain way. All right, so these are all the problems that can happen as a result of being in zero gravity. And some of them, other than looking clumsy and falling, can be pretty serious. Okay, you can get kidney stones, okay, as a result of being in zero gravity for a long time because your body's breaking down your bones. Okay, and that calcium builds up in your blood, and your kidneys have to try and filter it out. And when they do, if there's abnormally large amounts of calcium, it can form those crystals called kidney stones, and they can be not only very painful, but they can also be a serious health concern if you are millions of kilometers away from the nearest hospital. Okay? They can cause, they're a jagged little rock. Okay? If you've ever had a kidney stone, they're awful. Okay? They're a jagged little rock, and you have to pee them out. Okay? If they get really big, they can block your urinary tract, and that can back up into the kidney, and that can be serious. You can have organ, like kidney failure, okay, stuff like that. It can be very, very serious. The main concern is that they kind of slice up your urinary tract on their way out, and that can lead to infection, which, if you're millions of kilometers from the nearest hospital, an infection can be kind of a big deal. Right? So these are certainly a concern in zero gravity. Okay. You got your changed sensory input, okay, that confuses the brain. It causes occasional disorientation. Fluid distribution causes head congestion and puffy face. Okay, I'm going to show you some Chris Hetfield videos. You can hear him. He sounds congested in all of them. Okay, just really congested because of that. Okay, you got like your fluid redistribution shrinks your legs. Okay, you actually grow when you go into space. You can be like 2.5 inches taller in space because gravity's not pulling your joints together. Okay, you can kind of spread out so you can be taller in space. Okay, your weight-bearing bones and muscles deteriorate. All of that kind of stuff can be a big deal. All right, so what we want to do is create the spinning drum. Okay, if we create any part of the ship as a spinning drum, then we can create artificial gravity. So the person who's standing right here, they want to go in a straight line according to Newton's first law. But because they're on the inside of a drum, the drum pushes back towards the inside of the circle, okay, making them feel like they have weight. Now, what if I move towards the center? What will happen? If I move towards the center, what's happening to R? Getting smaller and smaller and smaller. Okay, so that's creating a centripetal force, right? I want that centripetal force to feel like this force, gravity. But if I'm in the middle of that spinning drum and R is 0, how do I feel? What happens when you divide by 0? What's my weight going to be? If I divide by 0, what's this going to equal? 0. Yeah. So if I'm in the middle, if I'm right here at the center, I'll be weightless. Okay? So most of the ideas that revolve around a spinning drum, okay, always have a central tube by which you access that drum, and then a ladder of some kind that allows you to descend from that central tube down to the inner surface of the drum. As you go down, you get heavier and heavier and heavier. Okay? So if I jumped, would I come back down? It depends how high you jump. Okay? It's not like on Earth. When I jump, if I get, even if I jump really high, I can jump to here and it's still 9.81. I'm still falling straight back down. Okay? But in a place like this, okay, if I can jump even a few feet and get halfway there, who knows? I might be able to get all the way across to the other side, okay? Or to the tube in the middle for sure. Right? The problem would be if you jump well enough, okay, that you would get all the way to the other side. But how will you be oriented when you get there? Yeah, you're going to hit your head. This would be the really cool thing. If you could time it right, you could take off and land from the same spot. Right? Because this thing is spinning while you're flying. Realistically, you couldn't because you would have inertia from being on that drum, right? So you would still be moving slightly in a circle, okay, as a result. But there's some pretty funky things that could happen with that. All right, so I'm going to show you some of the stuff they have to think about that we don't even think about, okay, here in a gravity environment. Like the one they don't have any pictures of, obviously, is the space john. Okay, they don't have any video of anyone using the space toilet. Okay, but just think about how important gravity is in the bathroom. Right? I mean, you want stuff to fall away from you when you're on the toilet. And there's no gravity, and it doesn't fall away from you anymore. Okay? Like, it's just a simple thing, guys. It's a simple thing, but man, if gravity's not there, the bathroom is a totally different thing. Okay? Everybody has their own tube. Okay? And it is, you pee into the tube. If it's urine, you pee into the tube. Okay? If you have to sit, so you're going number 2. Okay? Well, you have to sit. There's no standing to pee, guys, on the International Space Station. Gravity doesn't work. Okay? But what they do is they actually open it slightly to space, so the space john is a little windy. And it's the suction that makes sure everything falls away. Okay? It's a lot different. Okay? It's a zero gravity thing, so you got to think about that.